Thank you very much. In this talk, I will give our semi-classical model of quantum black holes formed slowly in a heat bath. To do that, let's first consider an object. The object can be in equilibrium with a heat bath of Hawking temperature. And in the vacuum region, the object evaporates in the time scale of a to the third. Here, a is Schwarzschild radius and LP is Planck length. By using this property, we can grow it up in a reversible way. More precisely, by changing the size and the temperature of the bath slowly, then we can grow it up in this way. The point is, the time scale of the operation should satisfy this inequality. If it is, then this process is reversible in a thermodynamic sense. The formed object should be very dense. In this talk, first we consider the Intellimetric of this object. To do that, we studied semiclassical Einstein equation. For simplicity, we assume conformal matter fields. Then we focus on the trace part of semiclassical Einstein equation. As you know, the trace part of energy momentum tensor for conformal matter fields is given by four-dimensional Weyl anomaly, this violet one. F, G, and Laplacian R are determined by curvatures. And coefficients CW, AW, BW are just numbers, which represent degrees of freedom of matter fields. The important point is this equation must be satisfied for any quantum state in this semiclassical Einstein equation, because as you can see, this is just a geometrical equation. So in this sense, the result obtained from this equation should be universal for any quantum state. In the following, we solve this equation directly to find Intellimetric of this object. But before that, let's estimate the curvature satisfying this equation. This equation can be rewritten schematically like this. Here, I used this estimation, okay? As you can see, this equation has two types of solutions. The type 1 is this one. Almost a curvature is almost zero, or more precisely, the order is given by this one. This type of solution is almost Schwarzschild, which contains a back reaction from small dilute effect. Dilute effect means the radiation around this object and vacuum polarization effect. The second type is very non-trivial. The curvature is order 1. More precisely, the order is 1 over NLP squared. Plugging this value into this equation, as you can see, this equation indeed is satisfied. The point is, h bar appear in the denominator, so this type of solution is a non-perturbative solution for h bar. And if you have many matter fields, then degrees of freedom n is large. Then this curvature is smaller than Planck scale itself. In this sense, this type of solution can describe a highly curved spacetime at semiclassical level. So this type of solution is a good candidate to describe in this interior dense region. Sorry. Of course, between two regions, the boundary exists. This boundary play a role of a surface of the object. I denote the position of the surface is just a capital R. Here, I approximate the exterior dilute region just by Schwarzschild radius, Schwarzschild metric, for simplicity. However, the interior region is very non-trivial. So we set the interior metric like this, AR, BR, unknown functions. Please note here, the interior is very dense, so the interior has a large redshift. This means any outside change will not influence the interior structure almost. Based on this physical expectation, we assume AR, BR are independent of the total mass. Let's assume this one. Now, we can determine the interior metric by solving this trace equation. First, we set the leading behavior for large R in this way. Next, we study the asymptotic behavior of the energy momentum tensor for large R and solve trace equation. This is the result. We obtain a class of solutions. N runs from 1 to 2, and a coefficient A0, B0 are related by this equation. This CW is this CW, okay? And furthermore, by connecting interior metric and exterior metric smoothly, then we can find the position of the surface here. The position is larger than Schwarzschild radius itself, so this object doesn't have a horizon, but the surface. And to restrict the possibility of the value of n within this range, we use consistency with Hawking radiation. Indeed, we can show the choice of n equal 2 is consistent with Hawking radiation. The first point is here. The object should emit some radiation because in order for the total system to become stationary, the radiation coming from the heat bath must be balanced with something emitted from the object. If this is true, in the vacuum region, the object starts to evaporate, and the size of the object, capital RT, decreases in time. Then here, we can check the energy flux behaves like this, A to the minus 2 and 2. So n equal 2 is consistent with Stefan Boltzmann law of Hawking temperature, this one. In the following, we focus on the case of n equal 2. For n equal 2, the interior metric can be written in this way. This metric has two parameters. One is sigma and the other is eta. Sigma is explicitly given by this one. CW is, of course, this CW, but eta is undetermined parameter. The value will be fixed later. But the eta takes this range. And here, our CW plays a role of degrees of freedom n. So here we assume CW is large. And then the position of the surface is determined explicitly like this. As you can see, the second term is much, much smaller than our Schwarzschild radius itself. So this object looks like a usual black hole from the outside. And here, a GTT it has a large redshift. So this is consistent with our initial assumption about independence for Intellimetric. In this slide, I will explain the feature of the metric. First, interior is not fluid. Energy density is a positive, and the radial pressure is a positive for this range of eta, and T theta theta tangential pressure is also positive, but this is almost Planckian. It is order 1 This order 1 value is much, much larger than radial pressure. In this sense, interior is very anisotropic and not fluid. However, this large pressure important because it supports the object against gravity. 2, if you focus on TR part of the metric, you can write it as ADS2 metric with this ADS radius. It is almost Planckian length. So interior metric is approximately ADS2 times S2. And the third point, if you estimate, evaluate curvatures, then you can find they are finite. So this object doesn't have singularity. Here, I will explain how Hawkinglike gladiation occurs from this object. First, as I said, in the vacuum region, the object should evaporate like this. If this is true, our sigma means our intensity of Hawkinglike gladiation, and eta appear here. So if eta is larger and larger, then the intensity is decreasing. This means eta is an log of gravity factor. Then for this geometry, we get this Penrose diagram for formation and evaporation process. Radiation is coming from the heat bath, and the object is formed, and it evaporates. Of course, this semiclassical treatment cannot describe final stage of the evaporation. Maybe this final stage has Planckian mass, and it could be described by some quantum gravitational state which decays soon. If this is assumed, then we get this fluid picture. But we can even in the semiclassical level, we can describe almost all parts of the object. This is a point. And in this background geometry, we can solve time evolution of our quantum fields in this way. Then we can show Hawkinglike gladiation indeed occur dynamically due to time dependence of the metric. The point is the time dependence makes particle. This is the final slide. Here, I will explain briefly how this Intellimetric satisfies all the components of energy moment Einstein equation. Discussion is self-consistent. Step 1, we set this metric as a candidate metric, just a candidate metric at this stage. And step 2, in this background geometry, we study n scalar fields and find candidate state psi. And step 3, we evaluate, renormalize energy momentum tensor for this candidate metric and candidate state. But as you can guess, this step 3 is very, very hard. However, if you use dimension regularization properly and use some perturbative technique in solving this field equation in this background geometry, then you can get renormalized energy momentum tensor systematically. And finally, step 4, equating left-hand side and the right-hand side, you can get a relation of eta, which determines self-consistent value of eta. In this procedure, we find our typical state of this object is our state in which our S waves are excited to express the collapsing matter. And modes with finite angular momentum emerge inside as bound modes in ground state for this geometry. interestingly, counting the possible number of excitation pattern for S waves, we can get this result. Entropy is just a area over 4. And using this bound mode, we can check self-consistently this large plexure. Okay, let me conclude. In this talk, we have seen this object, and this object has the surface at here, and it emits Hawkinglike gladiation, and it has entropy, this value. And Intellimetric is determined, this violet one, expressly. So we can say this object itself should be quantum black hole that is formed slowly in a heat bath. This is my message. And please note here, this picture is independent of quantum state and detail of exterior metric, because we have just solved trace part of semiclassical Einstein equation, which is state independent. I have some comment, but I should finish here. Thank you very much.
Thank you very much. Are there any questions? Please raise your hands or type them in chat. Yes, I think the first to raise their hand was Dan Jensen. Please go ahead.
Yeah, hi. Thanks for the talk. I was a bit, I mean, I'm slightly confused by this assumption that somehow the black hole is the is related to this regime where R is of the order 1 over the Planck length squared, and the exterior is somehow very lightly curved, and then you say, well, this black hole is formed but slowly in the heat bath. But how should I think about sort of the, I mean, if I start with a situation where the curvature is very low, how do I suddenly get how do I interpolate, so to say, between these two regimes during the formation process?
Thank you very much for your very nice question. I can give intuitive picture here. Yes. So here I can give just a intuitive picture for how the dense object is formed. You see, and here we suppose we have some object at some stage, okay? So, and in this formation process, our radiation, additional radiation comes to this object, right? So then, of course, this process is time dependent. So the geometry also are changing in time. This time dependence create very complicated effect, as you know. So, for example, particle creation or negative energy pressure, very complicated effect occur. And finally, but it can evolve like this, and this brick-like layer can be formed, just as suggested by 't Hooft. And repeated again, like this, we get this one. This is very intuitive picture. Is it okay?
Yes. Thank you. The next question is by Ignacio Reyes. Please go ahead.
Hey, thanks for the talk. So I wanted to see if I got one of your physical sort of conclusions right. So here you get a very large, like I say, at order 1 pressure. These are the components of the theta of the stress tensor,
Yes.
but without alluding to a very large central charge of the theory you're looking at. Or could you go to that formula again?
this Fitch formula?
Like you said that
This one?
Yeah. So this pressure can become very large independent of the number of fields that you have in 4D.
Yeah. So, as you can see, this you can take a trace of energy momentum tensor, or you can neglect this small value 1/r², 1/r². Essentially, trace is given by just this order 1 tangential pressure, right? So this tangential pressure almost same as here. This anomaly, trace anomaly itself, right? Because this is just a trace.
Right. And how do you get the other components?
Yeah, okay. So we need here. We need to perform this complicated program. Step 3 is very hard. So, but as I'm sorry, I don't have enough time. But for example, here we can set the energy momentum tensor like this on excitation part, which can be approximated just a classical part, and this non-trivial vacuum part. This vacuum part can be calculated directly dimension regularization. Our dimension regularization is very good because just introducing this something artificial 4+epsilon dimensional space-time. In this background geometry, we can solve field equation for each mode perturbatively in this way. And then we can calculate order by order regularized energy momentum tensor for all the components. So I can show just a little bit. So this is just a usual regularization technique. Yeah, here. This is very dirty, but analytically, you can pick up our UV divergence term and renormalization energy scale dependence part here, mu. This is energy scale. And the C is determined numerically, but this C is finite and very non-trivial. Yeah. In this way, it takes very long time and energy, but you can calculate it directly. Each component of energy momentum tensor in this background geometry.
Great, thank you.
Thank you.
And also there was a question by Julio.
Yeah, thank you, Yuki, for the talk. Just very briefly, I have a question about the magnitude of the space-time curvature inside this object.
Okay, just a moment. Here, yeah.
Is that magnitude Planckian, or is it below
Planckian? Yes, almost
okay.
Planckian. Yeah.
And when you mentioned the calculation of the renormalized stress energy tensor, there was some perturbative technique involved. Is that consistent with these Planckian curvatures?
Yeah. Yes. This is consistent because my perturbative technique is a perturbation for large R. So that is 1/r expansion intuitively.
Okay.
So the reading value is order 1 constant, and subleading is 1/r², and subreading 1/r to the 4th. Blah blah blah. Yeah.
Okay, I wasn't sure if it was perturbative in H bar and you had additional orders coming in. Okay, thank you.
Thank you.